there's no easy way to find Earth. So this direct imaging problem is difficult. And you know what, Terrestrial Planet Finder, with this concept, was funded on the order of $15 million a year for several years. And this telescope was so complicated. I still love it though, but it had an air budget of like 500 terms. And actually, there's people out there, my colleague Wes Traub at JPL, who will argue that this is the most mature of the ideas for a terrestrial planet finder. They have demonstrated in the lab that they can control with adaptive optics, a mirror. It's not the primary mirror, but a secondary mirror, to the level that's needed. And they have demonstrated in broadband white light that actually you can do this in the lab. And so he would be excited if we could cough up a few billion, it would be more than a few billion, to actually get this thing together and do it in space. I'm not sure when this would happen or if it would, but nonetheless, this is where we're at here. So you didn't look too frightened by this idea, but I'll tell you another thing that is one of my favorite ideas in astronomy. And everyone in astronomy knows I'm a big proponent of this. But you know what if you couldn't have a perfect telescope? That in fact, it turned out impossible to get that mirror so smooth to 1 angstrom as a function of time. How else could you do this? It turns out you could have any telescope in space. That could be the James Webb Space Telescope, for example. And instead of having that light cancellation dealing with diffracted light inside the telescope, you could deal with it outside the telescope. And that idea is the external culture. And here's a cartoon showing the external culture. You have a telescope, it has to be far from Earth to be in a thermally benign environment. And you have this occulter here in space. And did you see the shape of it? It's actually the same optimal shape as that other petal. And I hope this is a really exciting idea. It's very, very, very difficult. And what would happen is this, if you work out the numbers, has to be about 50 meters in diameter. And it has to be about 70,000 kilometers from your telescope. And you have to control this to within about a meter. And these petals here, that actually is not hard to control into a meter. It's actually not actually that hard to do, apparently. And these petals here, they can't bend too far, like in or out of the plane, because this is a diffraction pattern that's so important. But the point is that the light from the stars blocked out. And now there's this diffraction pattern all around you, all around the telescope. But it's dark. The planet can reach you because the stars are no longer bothering you. And this is a really interesting idea. People have gotten very excited about it. And like the original, it was called the Spurgle pupil for a while. This whole idea was worked out in 1985 by another French optician. There's a paper buried somewhere in the literature, but it was all worked out, all the details that I described. The person even got a shape like this, similar to this shape, mathematically. And it's all Fourier optics. Got the distances, a beautiful problem. So I wanted to update you about where this concept is, because it just sounds like pie in the sky, right? But there's some possibility this could be done with the James Webb Space Telescope. You can tell how excited I am about this. So the James Webb actually might be delayed. This is James Webb, it's the next generation Hubble Space Telescope. And one of my colleagues is also enthusiastic about this. It's really, he wrote to me, he's like, oh look, it looks like we might have time for the occulter after all. And it means that if you can develop this thing and get it off the ground and get it launched in time to work with another space telescope that's already planned, we'd have to start today. And we'd need millions and millions of dollars. People price tag it at $1 billion just for the occulter. But just to show you how people are serious about this, I have two pictures, real pictures. Here's one. This is Northrop Grumman test bed. I didn't take this photo. I actually took a couple pictures while I was out at Northrop Grumman. It's in LA. But I had to delete them because you're not supposed to take pictures there. I mean, they told me I could, and then they said I had to delete them because they do defense-related work. But what this is, it's about maybe, let's see, 200 to 300 feet piping. It's a tunnel to try to make this occulter in scale model. It's not exactly scale model because you want to preserve the Fresnel pattern. You don't actually want to preserve all the sizes. What you see here is the occulter. Remember, it's supposed to be 50 meters across. Here's the occulter. They made it in their own foundry. If you look, you have to probably squint, but you see the petal shape, same shape. So they make that. They have a laser light source, and they shine it in the occulter, and the camera's like all the way at the other end. And this is all the way at the other end. So they have this test bed that spans a couple of rooms, and they're one of the group that's trying to make this. So I went out there and I got to see this. But another thing they're doing is the actual precision with which you have to cut these petals. It's actually really challenging. I almost hate to tell you how hard it is. But you have to basically, it's like at the micron level. You have to cut these shapes to like tens of micron level. So another thing they're doing at Northrop Grumman, and if you go to an astronomy conference, they often bring it as a demo. They're trying to cut the spot in between. They're trying to demonstrate that they can make that shape in between those petals. We call the valley, like precisely, in a structure that actually is stiff enough. So people are really doing this. And there's one more exciting one. If you're let me think. If you're really interested in the discussion session that we're going to have at the reception, I can show you a movie, but I wasn't able to get the movie together for this. but I want to tell you about what they've done at JPL in terms of technology development. Who wants to guess what this is? Let's hear it. Someone has to be able to figure this out. In the background. These are my two students who just went out. Undergrad students who went out to present that exoplanet satellite. So want to guess what this is? Look. One of the pedals. So they made one pedal, and that's how big it would be, life size. And that wooden structure there is actually unfurled. They were experimenting how the pedal unfurled, because we have no launch vehicle that would take something that's 50 meters in diameter. You have to fold up and be deployed. And the movie that I have, if you're interested, you can ask me in the discussion section in the reception, actually shows it unfurling. And it's quite really fantastic, because you see all the JPL folks. If you work in astronomy, you'll recognize some of them. And they're all standing around, all really interested. And that's what I said in my last lecture. I said remember how I said 1,000 years from now, people will look back, and they will see us as the first generation of people who tried to find planets, who did find planets, and who hopefully are going to find planets like Earth. And I can just see them looking back at the video or this picture, it's sort of very primitive-like pedal. And there it is. And I wanted to tell you about this because I just want to convince you that people are working on the technology. And while there is no money for this project, there are certain key technological goals that have to be dealt with, and that people are trying to deal with the ones on the ground that you can deal with now. So to answer this part of the talk, summarize this part of the talk, the question was, when will we find another Earth? That's an Earth-like planet, and when we find another Earth, with the direct imaging, I said I would guess within 15 to 25 years. That 15 to 25 years is if we decide to do a terrestrial planet finder, either it's a full mission or just the occulter. And we have to start it really, really soon. If we want to do this in 15 years, we have to start now. It's a very, very challenging problem. If we just want Earth size or Earth mass, we can do that much sooner. Okay? But I really want to do this direct imaging problem, and I'm really, really excited about it. Okay, but I didn't come here to tell you about something that is so difficult and so expensive and so far away. That wouldn't really be justice to the field of exoplanets. So the next part of my talk is about when will we find another Earth part 2. And this is something that myself and others are also excited about. And for this particular question, we actually have decided to be more generous with our definition of Earth. And I liken this to the concept of finding a relative. Imagine for a minute you have an identical twin out there. It doesn't happen that often, but some people do have an identical twin they were separated from at birth. Imagine what it would be like to meet that person, just like you. And that's what I think of the Earth twin, finding the Earth twin. But now imagine for a minute that instead of the identical twin, you're going to find a long-lost cousin. It's someone from a different generation, from a different country. They don't speak the same language. They're much older or much younger. You can't really relate to them at all. But they're still a relative. And that's how I see this problem. And this problem is finding the big Earth around a small star. And this is consuming quite a lot of the field of exoplanets right now. And it relates to the idea of the so-called habitable zone or Goldilocks zone, whereby if we want to find a planet with surface liquid water, terrestrial planets are heated by the star. They're heated from the outside. So here I'm showing you a schematic. Sun, Earth, and here's the Earth at some distance from the star. But we have a lot of stars. Most stars are actually small stars. We call them M stars, low luminosity stars. And their energy output is so low that if the planet was going to have liquid water, it would actually be quite close to the star. And a big Earth, close to a small star with liquid water, is actually easier to detect in almost every single way except for direct imaging. And what people are banking on here is that they're going to be able to find a transiting big Earth around a small star and follow up the atmosphere, especially if it's hydrogen rich. And we'll look at the atmosphere in the future with the James Webb Space Telescope. So this is a huge field of exoplanets right now. And I'm going to talk about that for a few minutes. Now I'll just talk about transits for a second. So for Earth to transit the Sun, the probability is related to the distance from the star and the size of the star. So it's 1 to 200. If every star had 1 to 200 would transit. Period is 365 days, so it will take you a year. If it transits, you have to wait another year. So if you're a student, then you have to wait 1 year each time. It's a long time. If you're lucky, you'll have time. Otherwise, it's going to be a problem. And the transit depth is 1 part in 10,000. For the big Earth around a small star, everything's a lot easier. The probability is 1 in 50, or even less, actually. Period is now 13 days, and the transit depth is 1 in 1,000, which we can actually do from the ground. And this was really good, actually. This makes it quite easy, and people are really working hard. And now, actually, I have 1 or 2 really complicated slides only from a couple of conversations I had today. So this is just, you can blank out here if it's too complex. And this is sort of the basis of a lot of mine and others' computer codes, but it's just to put in perspective all the things you have to wonder about if you want to try to study the atmospheres of the exoplanets. We start with the wonder of the spectrum, and that has to do with the field called radiant transfer. It has to do with field rate and transfer. But to even do that, we need to understand what the atmosphere is made of. But to understand the atmospheric composition, we need to have a handle on chemistry and photochemistry and atmospheric escape. In the meantime, we also have to worry about atmospheric circulation, like how energy from the sun is distributed around the planet. And we have other issues in atomic and molecular physics and in cloud formation. So I could talk a lot about this because I love computer programming and it's a big part of my work. But instead of doing that, I will take you on a virtual trip to a habitable world. And a big Earth around an M star, this is what it would be like if we could go there. I will try to give you a description of what it would be like. First of all, we would be so close to the star that the sun would fill the sky, just like it is here. Now these super Earths close to the star, they are tightly locked. That is, we expect them to show the same face to the star at all times, just like the moon does to Earth. And this means, actually, practically, that the sun would be in the same place in the sky at all times. So then the question is, where would you want to live? If you're an astronomer, you want to live where it's always dark, unless you're a radio astronomer. Okay, but if you want to live in the daytime, you can live where it's always light. You can live, if you like sunset, you can vacation where the sun is setting. And actually, so that's kind of a cool thing. And then actually what I like about it is in astronomy, people often make a big discovery just as that star is about to go behind the sun. And so in this case, because your year is only 15 days or so, actually you'd see the stars again 15 days later, the one that you were interested in. And if there was a child here, I say for the children, it's really cool because 1 year is about 15 days, so you have your birthday every 15 days. This would be a disaster for the parents. Party for the child. And that's kind of the problem. So it actually would be a kind of fun place to go. Here's the artist is showing you, perhaps there are other planets that actually show up in the sky. Maybe the sky's a different color. That was purely an artist's license. We didn't work out any chemistry to show it would be like that. But we don't actually know what the hazes would be like. So here's the picture. Now actually, it might not be such a great place to visit after all, because these M stars, they tend to be active. Even the quiet ones often show flares. And these flares, think of like solar maximum, you get a big flare. This would be bad because it would disrupt our electronics. We might not be able to use our iPhones or play wireless video games. Some people think it would be detrimental for life, that mutations, kill life and you couldn't have any kind of stable, complicated life on the surface. That this could be a problem. Other planet formation theorists don't like these kind of planets because of the timescale for formation. They think it's not possible for asteroids to form and deliver water in time. And maybe these planets wouldn't have volatiles. But in fact, I always like to say that observers don't really care what theorists say. They will look because these planets are detectable now. And they will find these planets and we will follow them up and look at their atmospheres in the future. And we'll find what's out there no matter what is going on.